One more minute here. All right. First and foremost, there are three types of solution reactions. We're only going to deal with one in this chapter. That is a precipitation reaction. Why are we only dealing with one? Because this gets covered in a later chapter and this gets covered in a later chapter. We will come back to chapter 4 to supplement that, but they're covered in later chapters. So we're specifically going to talk about a precipitation reaction. First of all, what is the word precipitate, or what is a precipitate?
It's a solid that falls out of solution.
Okay, so what is something that was dissolved in an ion form and it re-solidified to form a precipitate. Now, unfortunately, at the bottom of 147, the very bottom of the second to last paragraph, says, as an aid in predicting the products of precipitation reactions, some simple solubility rules are given. Then what does it say? What does it say? Someone see it? You should memorize these rules. Alright, first and foremost, flip the page to those rules. Do you need to memorize them word for word? Absolutely not. Okay? You do not need to memorize them word for word. There is some trends, and I don't think it'll be as difficult as you might think. First first two are pretty obvious. There's a couple ones that are make a lot of sense, but there are a few that aren't quite as obvious. I want to make note of something. Some of them say, so 1 says soluble, 2 says soluble, 3 says soluble, but there's some exceptions. 4 says soluble, 5 says only slightly soluble, or marginally soluble. That means some of it dissolves, some of it does not. Okay? You need to write slightly if it's one where it says slightly. Okay? Now, here's what's happening. Kind of like what we talked about in the last question of your homework, where it was mixing two solutions together. Let's just say I've got, let's just go to the first problem here. Okay, so you already identified what a precipitate is. We're good with that, right? A precipitate is a solid that breaks out a solution. I'll hit on that more as we do this very first one. Okay, so first and foremost we have this guy. Now what does that mean? Yeah, it's aqueous, but what does it mean? It means it's dissolved in water. Okay, if these guys are dissolved in water, is there any solid there? They're in what form then? What form are they in?
Aqueous.
It's aqueous, but what form are they in? They're ions. Okay? So, first thing we should probably do is identify the ions. Now, notice it says two solutions are mixed. So, let's just say I've got two beakers here. We said that these are in ion form, so I know I have potassium ions here, and I know I have nitrate ions here. Okay, we're going to have to get good at identifying charge and whatnot, but I think you guys shouldn't have too much of a problem. Uncrisscross to find the barium charge, or just simply look at your periodic table for that one, and I should have twice as many chlorines. Yes? Okay. Now we know that those guys are already dissolved. So do I have a precipitate here or here? No. Now what it's saying is these two are poured into one. So now there's a possibility that potassium could come in contact with chlorine, yes? We got to figure out if that will precipitate out or not. Now, why did I not say potassium and barium?
So they're both cations.
They're both cations. They won't react, period. So you won't have to worry about that. But is it what?
But it could be barium.
Yep. It could be barium. Has a potential to react with nitrate. And so what they're asking you here is, when you mix these two, the things that weren't in contact, when they come in contact, is their solubility so low that they're going to precipitate out or not? Okay, that's essentially what they're asking in this type of problem. Does this make sense? Okay. So what you would do then, when you're looking at the rules to identify whether a precipitate will form, okay, let's look at this. First of all, it says most nitrate salts are soluble. Now, I'm going to say most is going to be in every single time for the context of what we're doing. So, will nitrate react with barium to form a precipitate? We don't even have to look at barium. If nitrate says it will never form it will always be soluble, then it's not going to react with something else. Unless there's some exception, but this one won't, there won't be. Okay? Then we got to identify, will potassium and chlorine precipitate out? Well, let's see if we can find the rule.
Rule number 2 says.
Okay, yep. So your potassium, really all your group 1 guys are going to be very soluble.
Also, rule 3 says the chloride ions.
Yep, and typically your halogens are very soluble due to their stronger polarity that would allow them to be attracted to water really well. Okay, now there are some exceptions there, but do we have any of those guys up here? No. So you would say for both of these, what?
No precipitates.
Okay. No PPT, that's how I identify or abbreviate precipitate things. No precipitate will form. And the reason why is potassium chlorine will not react to form a solid, and barium and nitrate will not react to form a solid. Okay, and you're going to find some trends with these rules. Like all the halogens, all the alkali metals are not going to be soluble. So that you don't have to worry about memorizing lithium, sodium, potassium. Just remember that group. Okay, do remember though that for the halogens there is a slight exception. So you got to keep that in mind.
Which one?
Does it say except containing sodium, lead, not sodium, silver, lead, and mercury? If that is there, they will probably precipitate that. Alright? I'll work on this next one with you, and then I'll have you guys do the last one. So really, if you want to draw a picture of beakers every time, you certainly can. But really, shouldn't it be the cation from one looking to see if it will react with the anion of the other? And then the cation of this one reacting with the anion of the other? Now we said that these guys are soluble by themselves, but when I mix them together, will a reaction occur? Well, we've already seen this guy. What does that tell you? Okay, so NaNO3 will not precipitate. Okay? All right, lead and sulfate. Let's see if we can find that guy. It says most sulfates are soluble, but there is a what? Exception. Okay, and I think you'll notice that lead and mercury are kind of exceptions for a lot of the rules. Okay, so most of the time when you see lead or mercury involved, it's probably going to be not soluble, and it will precipitate out. So for this, we would say PbSO4, that's 2 minus, will precipitate out. Questions so far? Everyone see why it will precipitate out? Emily?
It's not soluble.
Wait, soluble means
It's dissolved.
yeah.
Yep.
So it says most sulfate salts are soluble.
Yeah, but then it says notable exceptions are.
So do we memorize those?
We have to know the exceptions? Yeah.
I think we have to memorize this for the test.
I wouldn't. If memorizing makes you comfortable, yes. But you have to know it. Yeah. So, yeah. I would just look at big picture trends and not focus too much on, memorizing every word of that. If that makes sense. Like, do you have to memorize, like, group 1? There isn't even, I guess, Yeah, there isn't even any exceptions for that one. The only thing you'll probably have to worry about are the exceptions, to be honest. Okay, why don't you guys do the next one on your own? Oh, shoot. I got an answer?
Iron hydroxide would precipitate out.
Yeah, but be specific, slightly precipitate out. Yep. Yep. You get more practice with this on your homework. Really, this is just getting yourself. It's like a sig fig type of thing where familiarize yourself with the rules and it's not too hard. Right? Okay?
We have to do like village.
I mean, it's going to be multiple choice tests, so you'll have all of it. I'm trying to think what's on your. Oh, I did not give you any room. You might want to pull out a blank sheet of paper for this next problem.
But we only have 2 choices. So.
I could say no precipitate, both precipitate, one precipitates, the other precipitates. There's a lot of options. Okay? So this is a review from last chapter. Or not last chapter, last year. So I'm going to go through one example. I don't think I need to go through too many more. We've got formula equation. This would be like the overall complete balanced equation like you would see if you were balancing a chemical equation. Complete net ionic equation is taking all of those compounds and breaking them up if they're aqueous into their ions. The non-ionic equation is going to be removing the spectator ions, or the ones that do not participate directly in the reaction. So let me close this. You might want to pull up, either find a spot to do this. So I'm just going to give you the formula equation, and that's usually what you'll start with. They'll usually give you the balanced chemical equation, so that's what this guy is. K2, 4. Something wrong?
For A.
No, this is a completely new one. It's not on the notes. We're probably not going to get to that problem. I want to do one where I show you all of it.
Okay.
Okay? I guess A and B would be pretty difficult because you actually have to write the whole thing out and balance it, and then. But you guys already know how to do that, so I'm not going to focus too hard on that. That's the formula equation. I'm going to show you the complete ionic one in here. What that means is anytime you see aqueous, we know that it's in what form? Ion form, okay? So we need, I mean, this is really not an accurate depiction of what's happening because it's not in the combined form. So we need to break those up into their ions. That results in 2 things: knowing the charge and knowing how many of those ions you have. You find the charge by uncrisscrossing or looking at the periodic table, depending upon whether it's one that you can just look at the periodic table or not. Do we know the charge of potassium? How many of them do I have? 2. Do I write it here or here? I'm going to put it as a coefficient because it's an ion. You're not going to have, unless it's a polyatomic ion, you're not going to have multiple things combined. Okay? Aqueous plus, what's the charge of chromate? Don't know it, uncrisscross.
Two minus.
2 minus, and I only have one of them. Yeah? Make sense so far? Alright, charge of barium and how many?
1, 2 plus, right?
Cation? Ron, how many nitrates and what's the charge?
2, and then each nitrate is 1 minus, right?
Yep.
This is an expanded form.
Do you take out the solid?
No, if it's a solid, you do not put it in ion form, you just write it as what it is. Just leave it together because it's together, it's a solid. So we're only breaking the ions into their ions, not the solid. Alright, now we got a coefficient here, so we gotta think that this coefficient applies to everything, right? So we already know potassium's positive, but I have 2 of them. And I already know nitrate is negative, but I also have 2 of them. I should rotate this. Okay, do you remember this from last year? Okay. This is really important though, because being able to do this and identifying charge and coefficient is important for much later on. So this is a big deal. And the last one is net, which simply says take out the spectator ions, and the spectator ions are essentially the guys that don't do anything and they remain as ions on both sides. Okay, so what ions up here stay the same from the beginning to the end?
Potassium and nitrate.
So those would go bye-bye, that would go bye-bye, and your net would be what is left over, what is actually reacting.
0.
This is going to be more busy work and probably difficult, but it's still important for when we have to be able to do this before we can get to the more difficult math stuff. Okay? Now, maybe I could have done A or B on your notes, but it would have taken us a little bit longer to write the equation first and then balance it. And we only got 1 minute, so the only difference between what I showed you and what is in your notes is I gave you this versus you would have had to have wrote it up correctly. So remember, the whole chemistry builds on itself, and that we can't get away from writing formulas correctly and balancing equations correctly. Nice thing is you really get to know it pretty well once you do it all the time.
It's funny that you say chemistry builds on itself. That's literally what we're doing right now. Chemicals building themselves.
Okay?
No way.
We're getting the new stuff. Don't worry, we'll get the new stuff.
I'm not worried.
You're not excited for the new stuff?
No.
The hard stuff, or the old stuff is hard enough? Or